This is a video for AQA Further Pure Mathematics, Calculus section 3.1, where we're looking at differentiating arcsin x. Well, firstly, a reminder that when we are talking about the inverse of a sine function, then there are two ways of writing that. One is to use the idea of arcsin, and the other sine minus 1. Both of these are in common usage. It's important, if you're using the second one, to remember that sine the minus 1 of x is the inverse sine, and it's not used in the same way as, for example, x to the power minus 1, which is then the reciprocal 1 over x. So this minus 1 notation in trigonometric functions is reserved for the inverse of those functions. Throughout these presentations we're going to be using arcsin type of notation. Let's consider the graph of y equals arcsin x for a moment. We can produce this by reflecting y equals sine x in the line y equals x, of course, as we can for any inverse function. However, when we do that, we have to restrict the range of the function to lie between negative pi by 2 and pi by 2. This means that for each value of x, there will be only one value of y. The other thing which is worth noting, and we'll be using later on in the presentation, is the fact that the gradient of y equals arcsin x is clearly positive for all values. In other words, the derivative dy by dx is greater than or equal to 0. So now what I want to do is to consider that if y is equal to arcsin x, can we find dy by dx as a function of x? Well, the way to proceed is to realize that if y equals arcsin x, then we can take sines of both sides, so that sine y must be equal to x. Arcsine and sine are inverse functions of each other, so therefore sine of arcsin x is just equal to x. We can now differentiate both sides of this with respect to x, but of course on the left hand side we're going to need to use implicit differentiation. So differentiating sine y gives us cosine y multiplied by dy by dx. And that must be equal to the derivative of x, which is 1. We can then rewrite that to say that dy by dx must be equal to 1 over cos y. But we'd like to get this as a function of x. But we can do that by using the trigonometric identity that cos squared plus sine squared is equal to 1, and therefore cosine of y must be 1 over the square root of 1 minus sine squared y. But of course there'll be two of those, plus or minus. Sine squared y from above is equal to x squared, and therefore we've shown that dy by dx is equal to 1 over plus or minus the square root of 1 minus x squared. But from the graph that we were looking at earlier, we know that dy by dx is greater than or equal to 0. It's always positive. And therefore we can ignore that negative sign and say that the derivative of arcsine of x must be equal to 1 over square root of 1 minus x squared. So let's just look through that again very quickly. We used the idea of y equals arcsine x to mean that sine y must be equal to x, and then implicit differentiation. And then once we've done that, we've used the trig identity here to give us that cos y is the square root of 1 minus sine squared y. This is a general method that you'll see repeated in other videos. Now let's go back, now that we know what the derivative is, and consider how that compares to the graph that we had earlier. We know that we've got 1 over the square root of 1 minus x squared for our derivative, and therefore if we put x equal to 0 and we look at the gradient here at the origin, we can see that that must be equal to 1, so that tangent at the origin there is the line y equals x. So as the value of x ranges between -1 and 1, we can see that the square root of 1 minus x squared must be less than or equal to 1, and therefore the derivative, which is 1 over that, must be greater than or equal to 1. So you can see therefore that the shape of the graph very clearly is agreeing with the derivative that we found algebraically. A similar method can be used for a more general derivative, this time where we've got arcsin x over a, so that we can then write that sine y is equal to x over a, differentiating cos y dy by dx is equal to 1 over a, and therefore dy by dx must be equal to 1 over a multiplied by cosine of y. We can then use the same idea of the trig identity that we did earlier to say that this is equal to 1 over a multiplied by the square root of 1 minus sine squared y. Taking the positive root there again, because we know that the derivative must be positive. We can substitute for sine squared y being x squared over a squared, so that this then is equal to 1 over a multiplied by the square root of 1 minus x squared over a squared. We can take the a inside the square root, so we're going to go into here with that a, which then will give us a squared when it's inside the square root, so this is equal to 1 over square root of a squared, and then just minus x squared. So we therefore got that the derivative of arcsin x over a is equal to 1 over the square root of a squared minus x squared. In summary then, we found that the derivative of arcsin x is 1 over root 1 minus x squared, or a more general result, arcsin of x over a is 1 over root a squared minus x squared. You'll see how we use these results later when we look at integration. That's the end of this particular video. In the next one we'll be looking at differentiating arctan x.